On a clear autumn night, you can see the Andromeda galaxy with your naked eye. A faint smudge of silver light hanging in the darkness, seemingly close enough that some distant future version of humanity might actually go there. After all, it is our nearest major galactic neighbour, the galaxy next door. But that phrase hides a truth so extreme it breaks the human mind. The light touching your retina right now left Andromeda 2.5 million years ago, when your ancestors were still chipping stone tools on the African savanna, and light is the fastest thing in the universe. The distance to our closest galactic neighbour is not merely large, it is a wall, an abyss so vast it turns the word journey into a lie. If this kind of deep space storytelling changes how you see reality, do me a favour and consider hitting that like and subscribe button. It helps more than you know, and it's always appreciated. Now, settle in, get yourself comfortable, let's begin. Go outside tonight, find the constellation Cassiopeia, that crooked W of stars scratched across the northern sky. Now slide your gaze slightly downward and to the right. If the sky is dark enough, if you have escaped the sodium glow of city lights and the air is clean and steady, you will see it. A faint smudge, a tiny cotton wisp of silver light pressed against the blackness. It does not look like much. It looks like a thumbprint left on glass, or a small cloud that forgot to move. Most people glance past it without a second thought, but that smudge is not a cloud. It is not a nebula. It is not a cluster of nearby stars blurred together by distance. That faint glow is an entire galaxy. 1 trillion stars burning across 200,000 light-years of space, so far away that the light entering your eye tonight has been travelling since before your species existed. And yet there it is, visible without a telescope, without binoculars, without any technology at all, just your naked eye and a clear night. The Andromeda galaxy is the most distant object a human being can see without assistance. It has been hanging in our sky for as long as humans have looked upward. It was recorded over 1,000 years ago, in 965, by the Persian astronomer Abd al-Rahman al-Sufi, who described it in his Book of Fixed Stars as a small cloud. He had no idea what he was looking at. Nobody did. For nearly a millennium after al-Sufi's observation, Andromeda remained a mystery catalogued alongside actual nebulae and star clusters, as though it were just another smear of gas within our own Milky Way. Charles Messier, the French comet hunter, listed it as the 31st entry in his famous catalogue of objects to avoid when searching for comets. Messier 31. A nuisance, a distraction, a fuzzy patch that was definitely not a comet and therefore not worth his time. The irony is staggering. What Messier dismissed as a cataloguing inconvenience turned out to be the single most important object in the history of cosmology. Because Andromeda is not inside our galaxy. It is another galaxy, entirely. And the story of how we discovered that fact rewrote everything humanity believed about the size and structure of the universe. For centuries, astronomers assumed the Milky Way was everything. The entire cosmos, every star, every nebula, every glowing patch of light belonged to one vast system, and beyond its edges lay nothing but infinite empty darkness. The so-called spiral nebulae, those elegant pinwheel shapes visible through increasingly powerful telescopes, were assumed to be swirling clouds of gas within the Milky Way, perhaps regions where new stars were forming. Andromeda was considered the largest and brightest of these spiral nebulae. Beautiful, certainly. Scientifically interesting, maybe. But local. Contained. A feature of our galaxy, not a rival to it. This assumption felt so natural that it became doctrine. The universe was the Milky Way, and the Milky Way was the universe. The tension between those who believed the Milky Way was everything and those who suspected otherwise came to a dramatic head on April 26, 1920. On that evening, inside the Baird Auditorium of the Smithsonian Museum of Natural History in Washington, two astronomers stood before an audience and argued about the size of the universe itself. Harlow Shapley, a young and ambitious astronomer from the Mount Wilson Observatory, defended the prevailing view. The Milky Way, he insisted, was enormous, far larger than previous estimates suggested, and the spiral nebulae, including Andromeda, were minor features within it, clouds of gas perhaps, star-forming regions maybe, but local, contained, part of our system. On the other side stood Heber Curtis, an older and more cautious astronomer from the Lick Observatory, who argued that the spiral nebulae were not inside the Milky Way at all. They were island universes, entire galaxies in their own right, separated from us by distances so vast that the Milky Way was merely one among many. The event became known as the Great Debate, and it was not a polite academic exchange. The stakes were existential. If Shapley was right, the universe was one galaxy, unimaginably large but singular, and humanity lived at a knowable address within a comprehensible structure. If Curtis was right, the universe was something else entirely, a wilderness of galaxies stretching in every direction, each one a sovereign island of stars separated from its neighbours by chasms of empty space. Neither man had the evidence to settle the argument that night. Shapley had overestimated the size of the Milky Way by a significant margin, which made it easier for him to argue that the spiral nebulae could fit inside it. Curtis had correctly intuited that the nebulae were extragalactic, but his distance estimates were rough and his evidence circumstantial. He had observed novae in Andromeda that appeared far dimmer than novae elsewhere in the sky, which suggested Andromeda was extraordinarily distant. He had noticed dark lanes crossing the spiral nebulae that resembled the dust lanes in edge-on views of what he believed were other galaxies. The clues pointed outward, toward a universe far larger than anyone was comfortable imagining. But the clues were not yet proof. The audience that night could not have known that both men were partly right and partly wrong, or that the question they debated would be resolved within 5 years by a third astronomer using a telescope more powerful than either of them had access to. But the Great Debate matters for this story because it captures the last moment in human history when it was still scientifically respectable to believe the universe was small. Before 1920, a serious astronomer could stand before colleagues and argue that everything that existed fit inside a single galaxy. After Hubble's discovery 5 years later, that position was dead. The universe exploded outward, not physically, but conceptually, from one galaxy to billions, from a comprehensible structure to an incomprehensible expanse. And the object that detonated that explosion was the faint smudge of light in the constellation Andromeda that Messier had dismissed and Al-Sufi had recorded 1,000 years before. Then Edwin Hubble shattered everything. In 1925, using the 100-inch Hooker telescope at Mount Wilson Observatory, the most powerful instrument on Earth at that time, Hubble identified individual stars within Andromeda. Not just any stars. He found Cepheid variables, a special class of pulsating stars whose brightness fluctuates in predictable cycles. Henrietta Leavitt had already demonstrated years earlier that the period of a Cepheid's pulsation is directly linked to its intrinsic luminosity. Measure the pulsation period and you know how bright the star truly is. Compare that true brightness to how dim it appears from Earth, and you can calculate the distance. Hubble measured Andromeda's Cepheids, and the result was impossible. The spiral nebula was not inside the Milky Way. It was far outside it, a separate island of stars floating in the void at a distance so extreme that every previous map of the cosmos was instantly obsolete. The universe did not end at the edges of the Milky Way. The Milky Way was just one galaxy among what would turn out to be trillions. And Andromeda was the first proof. That discovery did more than expand the map. It permanently redefined humanity's relationship with scale. In a single calculation, the known universe went from one galaxy to at least 2, and soon after to millions, and eventually to the 2 trillion we estimate today. Every step in that expansion started with Andromeda, It was the first rung on the cosmic distance ladder, the gateway through which we glimpsed the true architecture of reality. And even now, a full century after Hubble's breakthrough, Andromeda remains the most important galaxy in astronomy apart from our own. It is our laboratory, our mirror, our nearest example of what a major spiral galaxy looks like from the outside, something we can never see for our own Milky Way because we are trapped inside it. Consider what Andromeda actually is. It is a barred spiral galaxy, similar in broad structure to the Milky Way, with prominent spiral arms winding outward from a central bar-shaped core, meaning it has a central bar-shaped structure formed by stars and prominent spiral arms winding outward from that core. It spans roughly 200,000 light-years across, which makes it comparable in size to the Milky Way, though some measurements place Andromeda slightly larger in extent. Its total stellar population is estimated at approximately 1 trillion stars. 1 trillion. That is roughly 2.5 to 5 times the number of stars in our own galaxy, depending on which estimates you use for both. Among those trillion stars are millions of stellar nurseries, countless planetary systems, ancient globular clusters orbiting its halo, and a supermassive black hole at its center, weighing in at roughly 100 to 200 million solar masses, dramatically more massive than our own Sagittarius A star, which tips the scales at about 4 million solar masses. Andromeda is not just a galaxy, it is a titan, the largest member of our local group, the gravitational family of roughly 100 known galaxies to which both the Milky Way and Andromeda belong. In January of 2025, the Hubble Space Telescope completed the largest photomosaic in its history, a panoramic image of the entire Andromeda disk that resolved more than 200 million individual stars. 200 million points of light, each one a sun, individually identified and catalogued across a galaxy sitting 2.5 million light-years away. Hubble can only detect stars brighter than our Sun. The remaining hundreds of billions of dimmer red dwarfs and faint stellar remnants lie below its detection threshold. Even the most detailed portrait ever made of Andromeda captures only a fraction of its true population. And every single grain of detail in that portrait belongs to a galaxy we call our neighbor, a galaxy that appears so close and so knowable that the distance separating us from it barely registers as a concern. Right next door. That is the phrase that keeps appearing in every astronomy textbook, every documentary, every press release. Andromeda, our nearest major galactic neighbor. The galaxy next door. The closest large spiral. These phrases are technically correct and profoundly misleading at the same time, because they suggest a kind of closeness, a proximity, that implies reachability. When you call something a neighbor, the human brain files it into a category of things that are nearby, things you could visit, things separated by a distance that effort and time could overcome. Your neighbor is across the street, the next town is down the highway, the next country is across the ocean. Difficult, maybe. Expensive, perhaps. But achievable. The language of neighborhood implies that Andromeda is the galactic equivalent of the house next door. Far, yes, but fundamentally the same kind of distance we already understand, just scaled up. And that intuition is the lie this entire story is built on. The distance to Andromeda is approximately 2.5 million light-years. Different measurement techniques yield slightly different values. Cepheid variable methods give approximately 2.51 million light-years. Eclipsing binary methods from 2005 give 2.52 million light-years. The tip of the red giant branch method yields 2.56 million light-years. Infrared surface brightness fluctuation methods give 2.57 million light-years. Averaged together, the current scientific consensus settles at roughly 2.54 million light-years, plus or minus about 110,000 light-years of uncertainty. For simplicity, and in accordance with NASA and ESA standard references, we will use the rounded figure of 2.5 million light-years. That is the number. 2.5 million light-years. It sounds almost manageable when you say it quickly. 2.5 million, you have heard larger numbers. The national debt is trillions. The human body contains 37 trillion cells. Compared to those figures, 2.5 million sounds practically modest. But light years are not dollars or cells. A single light year is the distance light travels in 1 year, moving at 186,000 miles per second. In 1 year, a photon crosses approximately 5.88 trillion miles. 1 light year equals nearly 6 trillion miles. Already the number becomes violent, but you can still hold it, barely. 6 trillion miles. Enormous, but expressible. Now, multiply that by 2.5 million. The distance to Andromeda is approximately 14.7 quintillion miles. Written out, that is 14,700,000,000,000,000,000 miles. If you tried to write that number as a line of individual mile markers spaced 1 inch apart, the line would stretch further than the distance from Earth to Jupiter. The number itself becomes a kind of weapon against intuition. It is too large to mean anything. It sits in the mind like a stone you cannot lift, and eventually you stop trying. You round it off. You file it under far away and move on. And that surrender is exactly where the real terror begins. Let us try to make it tangible using something familiar. Start with the Earth. Start with home. The average distance from the Earth to the Moon is about 239,000 miles. A beam of light covers that gap in roughly 1.3 seconds. If you could drive a car to the Moon at highway speed, the trip would take about 5 months. Astronauts in the Apollo missions crossed that distance in about 3 days. The Moon is close. It is the closest celestial body to Earth, and we have physically been there 6 times. Now stretch outward. The Sun sits approximately 93 million miles from Earth. Light crosses that distance in about 8 minutes and 20 seconds. A car driving at highway speed would need roughly 170 years to reach the Sun. We have never been there. We have sent a probe, the Parker Solar Probe, which has swooped to within 3.8 million miles of the Sun's surface. At its closest approach, it became the fastest object humanity has ever built, reaching 430,000 miles per hour. Remember that number. We will need it later. Now move further out. Mars, at its closest approach, sits about 34 million miles away. Our fastest rovers take roughly 7 months to get there. Jupiter lies about 365 million miles from Earth at its nearest. The Juno spacecraft, traveling at speeds exceeding 165,000 miles per hour during its Jupiter orbital insertion, still took 5 years to make the journey. Saturn, the ringed jewel, sits roughly 746 million miles away at closest approach. Cassini took nearly 7 years to arrive. Neptune, the outermost major planet, orbits at an average distance of about 2.8 billion miles from the Sun. Voyager 2, the only spacecraft to visit Neptune, launched in 1977 and did not reach Neptune until 1989. 12 years. And Voyager 2 had the advantage of gravitational slingshots around Jupiter and Saturn to boost its velocity. Now consider the edge of our solar system. The Oort cloud, a vast shell of icy objects that marks the gravitational boundary of the Sun's influence, is estimated to extend out to roughly 1.6 light-years from the Sun. That is approximately 9.4 trillion miles. No human probe has ever come close to reaching it. Voyager 1, the most distant human-made object, launched in 1977 and currently travelling at roughly 38,000 miles per hour, has covered about 15 billion miles in nearly 50 years of flight. It has crossed barely more than 0.1% of the distance to the Oort cloud's outer edge. 50 years of flight, and it has not even covered 2/1000ths of the journey to the boundary of our own solar system. Our most ambitious robotic explorer, travelling continuously for half a century, has barely scratched the edge of our own solar system's backyard. And the solar system is not the galaxy. The solar system occupies a tiny pocket of space, roughly 2 to 3 light-years in effective radius. The Milky Way galaxy stretches 100,000 light-years across. The solar system fits inside the galaxy the way a single bacterium fits inside a cathedral. Everything you have ever known, every planet you have ever seen in the night sky, every mission humanity has ever launched, every distance any human-made object has ever traveled, all of it exists within a space so small relative to our galaxy that it essentially rounds to zero. And Andromeda is not across the galaxy. Andromeda is outside the galaxy, far outside it. 25 times the entire width of the Milky Way. That is not a longer version of the same journey. That is a different category of distance entirely. A category so extreme it makes the previous numbers feel like measurements of your living room. This is where the first crack appears in the illusion of proximity. When astronomers say Andromeda is our nearest major galactic neighbor, they are telling the truth. It is the nearest large spiral galaxy. There is no closer major galaxy. The next comparable targets, galaxies like Centaurus A or Messier 81, sit roughly 12 to 14 million light-years away, 5 to 6 times farther than Andromeda. In the catalogue of major galaxies, Andromeda really is next door. But the word nearest does not mean near. It does not mean close. It does not mean reachable. It means only that everything else is worse. Andromeda is the least impossibly far major galaxy. And that distinction, the difference between nearest and near, contains a horror that will only deepen as we begin translating the numbers into terms the human mind can actually feel. There is something else worth understanding about Andromeda's position that makes the distance even more disorienting. Andromeda is not hidden. It is not buried behind dust clouds or lurking at the edge of detectability. It is one of the most prominent objects in the sky. On a clear autumn night from the northern hemisphere, the Andromeda galaxy covers a patch of sky roughly 6 times the apparent diameter of a full moon. If your eyes were sensitive enough to detect its full extent, it would appear as an enormous, elongated glow dominating the constellation, far larger than any other deep sky object visible without a telescope. We photograph it routinely. Amateur astronomers capture it with consumer cameras mounted on backyard tripods. It appears in phone apps, star maps, desktop wallpapers. It is familiar. It is accessible. It is right there. And that visibility is the cruelest part of the illusion, because everything about the way Andromeda presents itself to human senses suggests proximity. You can see it, so it must be close. You can photograph it, so it must be reachable. It fills the sky with light, so it must be a journey of some finite, meaningful length. Your instincts built over millions of years of evolution on the African savanna, where if you could see something you could generally walk to it, tell you that Andromeda is part of your world. Your instincts are catastrophically wrong. The light that makes Andromeda visible tonight is ancient beyond comprehension. Every photon that reaches your retina from that soft glow departed Andromeda approximately 2.5 million years ago. When that light began its journey, the entire genus Homo was barely established on Earth. Homo habilis, the earliest species in our lineage widely recognized as human, was chipping crude stone tools in East Africa. There were no cities, no languages, no agriculture, no written words, no concept of a galaxy or a star or a photon. That light has been crossing the void of intergalactic space continuously, without stopping, at 186,000 miles per second, every second of every day, for 2.5 million years. And it arrived tonight, on your retina, while you stood in your backyard looking up. The journey that light just completed is longer than the entire history of the human lineage, and light is the fastest thing that exists in the physical universe. Nothing outruns it, nothing matches it. It is the absolute hard, non-negotiable speed limit of reality. If even light needs 2.5 million years to make the crossing, what does that say about anything slower? What does it say about a spacecraft? About a radio signal? About any physical object bound by the laws of physics as we understand them? The answer to those questions is where this story turns dark. Because the distance to Andromeda is not merely a very large number. It is not merely far in the way that Australia is far from Iceland, or Pluto is far from the Sun, or even Alpha Centauri is far from our solar system. The distance to Andromeda exists in a category of remoteness that has no analogue in human experience. It is a gap so extreme that it transforms the meaning of words like journey, travel, and distance themselves. But to feel that transformation fully, you need to see the numbers laid out one next to the other. You need to watch the ladder extend from the familiar to the impossible, rung by rung, until the rungs themselves become absurd. You need to understand how far away the nearest stars are, how wide our own galaxy is, and why even those staggering distances look trivially small compared to the chasm that separates us from the galaxy we call next door. That ladder is where we go next. Before we climb toward Andromeda, we need to understand where we are standing, not on Earth, not in the solar system. Those scales are already behind us. We have already established that the entire solar system, everything from the Sun to the outermost fringes of the Oort cloud, occupies a region roughly 2 to 3 light-years across. That is our backyard, our porch, the space we can plausibly call ours. Now we need to step off the porch and walk into the street. The street, in cosmic terms, is interstellar space, the gaps between stars, and those gaps are where human intuition begins to buckle under weight it was never designed to carry. The nearest star system to our Sun is Alpha Centauri. It is not a single star, but a triple system. 2 Sun-like stars, Alpha Centauri A and Alpha Centauri B, orbit each other in a tight gravitational embrace, while a smaller, dimmer red dwarf called Proxima Centauri orbits farther out and holds the distinction of being the single closest star to Earth. Proxima sits approximately 4.24 light-years from our solar system. Alpha Centauri A and B are slightly farther, at about 4.37 light-years. For simplicity, and because the difference is small enough to be irrelevant at the scales we are approaching, we will round and say the nearest star is roughly 4.25 light-years away. 4.25 light-years. Write it down. Hold it in your mind. It is the smallest, meaningful step beyond our own solar system, the shortest interstellar distance that exists for us, and it is already a number that should make you uneasy. Because 4.25 light-years means that a beam of light, racing at 186,000 miles per second, the fastest speed permitted by the laws of physics, takes 4 years and 3 months to cross the gap. That is not a travel estimate. That is not an engineering problem waiting to be solved. That is the hard floor of reality. No signal, no spacecraft, no hypothetical future technology that obeys the known laws of physics can cross that distance in less time than light itself. 4 years and 3 months at the universal speed limit. Minimum, non-negotiable. Now translate that into human terms. Voyager 1, launched in 1977, has been travelling through space for nearly half a century. It moves at approximately 38,000 miles per hour relative to the Sun. If Voyager 1 were aimed at Alpha Centauri, which it is not, the journey would take roughly 73,000 years. 73,000 years. All of recorded human civilization, every empire, every war, every invention, every book, every song, every life ever documented in written language, spans roughly 5,000 years. Voyager would need 14 times that entire span of history to reach the nearest star, and Voyager 1 is not slow by human standards. It is one of the fastest objects we have ever launched. It crossed the orbit of Jupiter in under 2 years. It reached interstellar space in 36 years. By any terrestrial measure, it is screaming through the void. And the void does not care. Let us try the Parker Solar Probe, the fastest human-made object in history. At its peak velocity during close solar approaches, the Parker Solar Probe reaches approximately 430,000 miles per hour. That is fast enough to fly from New York City to Tokyo in under a minute. At that speed, the trip to Alpha Centauri would still require approximately 6,600 years. Roughly the same amount of time that separates the present day from the earliest known smelting of copper in the ancient Near East. an era when writing had not yet been invented and the first true cities were still millennia away. Our fastest machine, burning through space at a velocity that makes intercontinental ballistic missiles look like drifting leaves, would need the entire length of ancient and modern history combined to reach a star you can see twinkling on any clear night, and Alpha Centauri is the closest one. It is the best-case scenario. Every other star in the galaxy is farther away, most of them enormously so. This is the first rung of the ladder, the nearest star, 4¼ light-years, already functionally unreachable with any existing or near-future technology. Already a journey measured not in human lifetimes but in the lifespan of civilizations. Hold that rung. Feel its weight. Now look up. The ladder goes much, much higher. Our Sun sits approximately 26,000 light-years from the center of the Milky Way galaxy, embedded in one of the galaxy's outer spiral arms. The Milky Way itself, our entire galaxy, stretches roughly 100,000 light-years across its visible disk. Some recent measurements suggest the full extent, including faint outer stellar halos, may reach 150,000 to 200,000 light-years. But the standard figure for the luminous disk remains approximately 100,000 light-years. Think about what that means. Light itself, moving at the cosmic speed limit, needs 100,000 years to travel from one edge of our galaxy to the other. If you stood on a planet orbiting a star at the far rim of the Milky Way and flashed a laser toward a planet on the opposite rim, the beings who received your signal would be separated from you by a temporal gulf of 100 millennia. Any reply they sent would take another 100,000 years to reach you. A single round-trip conversation across the galaxy would span 200,000 years. The entire history of Homo sapiens as a species fits comfortably inside that gap twice over. Now let us feel the scale another way. The Milky Way contains somewhere between 200 billion and 400 billion stars. At the lower estimate, if you assigned every star a single grain of rice, the pile would fill an entire concert hall floor to ceiling. All of those stars, all of those hundreds of billions of nuclear furnaces, each separated from its neighbors by light-years of vacuum, fit within a disk 100,000 light-years across. The stars are not packed tightly. The average distance between neighboring stars in our region of the galaxy is roughly 4 to 5 light-years, similar to the gap between our Sun and Alpha Centauri. In the dense central bulge near the galactic core, stars crowd closer together, perhaps a fraction of a light-year apart. In the sparse outer arms where we live, the gaps widen. But even in the most crowded stellar neighborhoods, space dominates overwhelmingly over matter. The galaxy is vast, but it is mostly vacuum, a shimmering web of emptiness with occasional pinpricks of fire. But those numbers describe the galaxy as though it were a static object, a map pinned to a wall. It is not. The Milky Way is a living machine, rotating, churning, breathing clouds of gas into stars and exhaling the ashes of dead ones back into the void. Our solar system orbits the galactic center at roughly 515,000 miles per hour. That sounds fast, and it is, by any human standard. But the galaxy is so large that even at that velocity, one complete orbit takes approximately 225 to 250 million years. Astronomers call this period a galactic year. In the 4.5 billion years since the Earth formed, our planet has completed roughly 20 orbits around the galactic center, 20 laps. In the entire lifespan of our world, we have circled our own galaxy only 20 times. When the dinosaurs went extinct 66 million years ago, Earth was roughly a quarter of the way through its current orbit. The Sun was in a completely different part of the galaxy. The constellations did not exist. The stars around us were strangers. Everything you see in the night sky tonight is a temporary arrangement that will dissolve and reform as the galaxy rotates, shuffling stars like a slow cosmic kaleidoscope that turns once every 250 million years. And yet even that immense orbital journey covers only a ring within the galaxy, not the full structure. Our orbit traces a circle roughly 160,000 light-years in circumference at a radius of 26,000 light-years from the center. The stars in the inner galaxy orbit faster. The stars in the outer arms orbit slower. None of them are sitting still. The entire disk is a whirlpool of 400 billion stars in constant motion, each one tracing its own elliptical path around a center defined by the combined gravitational pull of every other star, every cloud of gas, every scrap of dark matter in the system. The galaxy is not a place, it is a process. A gravitational engine cycling matter through birth, death, and rebirth across timescales so long that the engine itself appears frozen to any observer trapped within a single human lifetime. This sense of frozen motion is part of what makes the galaxy's size so difficult to internalize. Nothing appears to move, the stars look fixed, the spiral arms look permanent, the dust lanes look painted on. But all of it is flowing, and the flow is so slow relative to human perception that you could watch the sky for 1,000 years and never detect the shift. The nearest stars drift against the background by tiny fractions of a degree per century, detectable only by instruments like the Gaia Space Telescope, which has measured the precise positions and motions of more than 1 billion stars. Gaia revealed that the galaxy is not the orderly pinwheel of textbook illustrations. It is messy, warped, rippled by past collisions with smaller galaxies, its disk bent slightly like a record left in the sun. Streams of stars from devoured dwarf galaxies thread through the halo like scars from ancient violence. The Milky Way is not serene. It is a survivor of billions of years of gravitational combat, and its structure records every blow. Understanding this internal complexity matters for one reason. It establishes the galaxy not as a simple disk you could theoretically cross, but as an environment of staggering depth and scale. A structure so vast and so dynamic that even mapping it from the inside has taken humanity centuries and remains incomplete. We have spent 500 years with telescopes pointed at the sky, and we still do not know exactly how many spiral arms our galaxy has. We are still debating whether the Milky Way is a grand designed spiral with cleanly defined arms, or a flocculent spiral with patchy, fragmented structure. We are still discovering stellar streams, still mapping the outer halo, still revising the mass estimate upward as new data arrives. Our own galaxy remains partially unknown to us, and its full crossing would take longer than the universe has existed. This is the structure that Andromeda dwarfs by a factor of 25 in the distance separating them. To cross this galaxy at the speed of our fastest spacecraft would require a journey of unthinkable duration. At the Parker Solar Probe's peak speed of 430,000 miles per hour, traversing 100,000 light-years would take approximately 156 million years. That is longer than the entire span of time separating the present day from the late Jurassic period, when dinosaurs dominated every continent and the first birds were just beginning to evolve. Crossing our own galaxy, at the fastest speed humanity has ever achieved, would take a journey so long that the species that launched the spacecraft would almost certainly be extinct before it arrived. The Milky Way is not just big, it is big enough to make the word big feel like an insult. It is a structure so vast that no physical object bound by known physics could cross it within any time frame that preserves the identity of the civilization that attempted it. Light can do it in 100,000 years. Everything else fails. And now we arrive at the critical moment, the turn. The point where the ladder stops being steep and becomes something else entirely. Because everything described so far, every distance, every travel time, every impossible number, exists within our own galaxy. The nearest star, the galactic disk, the 100,000 light-year crossing. All of it is local. All of it is inside our home. And Andromeda is not inside our home. Andromeda sits approximately 2.5 million light-years away. The Milky Way is approximately 100,000 light-years across. This means the distance to Andromeda is 25 times the entire diameter of our galaxy. Imagine standing at one end of a football field. The far goal line represents the opposite edge of the Milky Way, 100,000 light-years away. Now keep that football field exactly where it is and ask how far away Andromeda would be at the same scale. The answer is 25 football fields away. Not 25 yards. 25 full fields laid end to end, each one representing the entire width of a galaxy containing hundreds of billions of stars. The gap between us and Andromeda is so large that you could line up 25 Milky Ways between here and there and still have room left over. This is not a difference of degree, this is a difference of kind. Interstellar distances, the gaps between stars within a single galaxy, are already staggering. They dwarf everything in the solar system by factors of thousands. But intergalactic distances dwarf interstellar distances by the same savage ratio all over again. Moving from the solar system to the nearest star is like stepping from a house into the surrounding city. Moving from one star to another across the galaxy is like crossing a continent. Moving from our galaxy to Andromeda is like crossing an ocean so wide that the entire continent you just traversed would be invisible from the far shore. Each jump upward on the ladder does not merely add distance. It multiplies it by orders of magnitude that make the previous level feel like a rounding error. Consider it from the perspective of emptiness. Within the Milky Way, the space between stars is vast but not absolute. Every few light years you encounter another sun, another gravitational well, another pocket of warmth and light. If you were somehow traveling through the galaxy, you would pass stellar neighborhoods, nebulae, star clusters, regions of dust and gas. The journey would be immensely long but punctuated by waypoints, landmarks, evidence that you are moving through a populated space. Between the Milky Way and Andromeda, there is almost nothing. The intergalactic medium, the material that fills the space between galaxies, is one of the most perfect vacuums in nature. Densities drop to roughly 1 atom per cubic meter or less. There are no stars to navigate by, no dust clouds to mark progress, no gravitational oases to rest in. Just emptiness stretching for 2.5 million light years in every direction. A void so pure and so enormous that it makes the spaces between stars feel like a crowded marketplace by comparison. The intergalactic medium between the Milky Way and Andromeda deserves a closer look, because its emptiness is not ordinary emptiness. Within a galaxy, the space between stars is already extraordinarily vacant. The interstellar medium contains roughly 1 atom per cubic centimeter, mostly hydrogen, which sounds sparse until you compare it to what lies between galaxies. The intergalactic medium in the local group contains roughly 1 to 10 atoms per cubic meter, not per cubic centimeter. Per cubic meter. That is 1,000,000 times emptier than the already nearly perfect vacuum between stars. For context, the best ultra-high vacuum chambers on Earth achieve densities of roughly 100 atoms per cubic centimeter, which is still approximately 10 million times denser than the intergalactic medium. The space between Andromeda and us is emptier than anything humans have ever artificially created. The space between Andromeda and us is emptier than anything humans have ever artificially created. It is among the most perfect vacuums in nature, surpassed only by the even more rarefied expanses inside the great cosmic voids between galaxy clusters. This emptiness is not just an absence of atoms, it is an absence of everything that makes space navigable. No stars to provide gravitational waypoints, no gas clouds to refuel hypothetical interstellar ramjets, no magnetic field strong enough to interact with, no dust, no radiation pressure, no structure of any kind that a traveller could exploit or orient by. The intergalactic medium is a desert without sand, an ocean without water, a darkness so thorough that if you were placed in the middle of it, the Milky Way would appear as a faint smudge in one direction, and Andromeda as a faint smudge in the other, and between them would stretch nothing, absolutely nothing. For over 1,000,000 light years in every direction around you, the universe would be functionally empty, a void so vast and so featureless that the concept of location itself would begin to feel meaningless. This is the medium through which any hypothetical journey to Andromeda must pass, not the relatively cluttered space between stars, where at least other suns dot the darkness every few light years, not the moderately sparse regions of the galactic halo, where globular clusters and stellar streams provide occasional points of interest. The actual intergalactic void. 2.5 million light-years of functionally perfect nothing. Even if a spacecraft could somehow achieve a significant fraction of light speed, it would spend millions of years drifting through an environment so empty that the nearest gravitationally significant object in any direction would be an entire galaxy. There would be no rescue, no resupply, no landmark, no reference frame except the fading glow of two distant spirals, slowly changing their apparent size over epochs of travel. The crossing would not feel like a journey through space. It would feel like a journey through the concept of emptiness itself, an experience of nothingness so absolute and so prolonged that even the word isolation fails to capture its texture. There are a few exceptions scattered within that void. The local group, our gravitational family of roughly 100 known galaxies, includes dozens of small dwarf galaxies floating in the space between the Milky Way and Andromeda. Satellite galaxies like the Sagittarius Dwarf, the Large and Small Magellanic Clouds, and Andromeda's own swarm of companions pepper the region. In April of 2026, astronomers announced the discovery of Andromeda 36, a newly identified ultra-faint dwarf satellite of Andromeda, located approximately 388,000 light-years from Andromeda's center, and roughly 2.5 million light-years from us. Its very existence underscores the scale of the space involved. An entire galaxy, however tiny, drifting in the abyss between two giants, so faint it was only just confirmed after being spotted during a visual inspection of survey images by an amateur astronomer. These dwarf systems contain anywhere from a few million to a few billion stars each. They are real structures, real galaxies in their own right. But compared to the void they inhabit, they are specks of foam on the surface of a dark ocean. Let us now lay the rungs of the ladder side by side, because the pattern they reveal is the entire point. Earth to the Moon, 1.25 light seconds, a distance humans have physically crossed. Earth to the Sun, 8 light minutes, a distance we have sent probes near. Sun to the outer edge of the solar system, roughly 1 to 2 light years, a distance no human probe has crossed even a fraction of. Sun to the nearest star, 4.25 light years, a distance that would require thousands of years with our fastest technology. Width of the Milky Way, 100,000 light years, a distance that would require billions of years with our fastest technology. Milky Way to Andromeda, 2.5 million light years, 25 times the entire width of the galaxy, a distance so vast that even measuring it in light years, a unit already designed for cosmic scales, produces numbers that feel hallucinatory. Look at the jumps between those rungs. Each one is not a gentle increase. Each one is a violent multiplication. From the Moon to the Sun, the distance grows by roughly 400 times. From the Sun to the nearest star, it grows by roughly 270,000 times. From the nearest star to the galactic edge, the distance grows by more than 20,000 times. And from the width of the galaxy to Andromeda, it grows by another factor of 25. Each step annihilates the previous step. Each rung makes the one below it seem almost trivially close. And Andromeda sits at the top of this particular section of the ladder, looming above every distance that came before it, separated from us by a gap that makes every other gap feel like a crack in the sidewalk. This is the structural truth that the phrase nearest major galaxy hides. When you hear that Andromeda is our closest galactic neighbor, your brain instinctively translates that into a kind of proximity. Nearest means close, neighbor means accessible, but the ladder shows you what nearest actually means in this context. It means the shortest impossible distance, the smallest version of a gap that no physical object can plausibly cross. The least extreme example of a category of remoteness so severe that it makes interstellar travel, itself already functionally impossible with current technology, look like a commuter flight by comparison. And there is something else the ladder reveals if you stare at it long enough. Notice where the largest conceptual break occurs. It is not between the solar system and the nearest star, although that jump is enormous. It is not between the nearest star and the far side of the galaxy, although that jump is worse. The largest conceptual break is between anything inside the galaxy and anything outside it. The jump from intragalactic to intergalactic distance is not just bigger, it is qualitatively different. Inside the galaxy, distances are measured in light years, maybe tens of thousands of light years. Those numbers are staggering, but they belong to a comprehensible category. A light year is 6 trillion miles. 100,000 light years is 600 quadrillion miles. You can write the numbers down. You can do the arithmetic. The quantities are savage, but they are expressible. The distance to Andromeda exits that category. 2.5 million light years is not a very large number of light years in the way that a very tall building is a very large number of floors. It is a number that reveals the existence of a new scale entirely. It tells you that galaxies are not arranged the way stars are arranged within a galaxy. Stars within a galaxy are separated by gaps of a few light years each, spread across a structure 100,000 light years wide. Galaxies are separated by gaps of millions of light years, scattered across a universe billions of light years across. The ratio of gap to object changes violently when you step from the stellar scale to the galactic scale. Stars within a galaxy are like houses in a dense city, relatively close compared to their own size. Galaxies within the universe are like isolated farmsteads, separated by hundreds of miles of empty desert. The spacing is fundamentally different. The loneliness is fundamentally deeper. This is why the distance to Andromeda is not just a bigger version of the distance to Alpha Centauri. It is a different animal, a different species of remoteness. The distance to Alpha Centauri is interstellar. It separates two stars within the same galaxy, two members of the same gravitational family, 2 points connected by the same galactic structure. The distance to Andromeda is intergalactic. It separates two galaxies across a void that belongs to neither, a gap so wide that it dwarfs both objects it separates. Interstellar distance is the space between rooms in a building. Intergalactic distance is the ocean between continents. Both are distances, both can be measured, but they are not the same thing. And treating them as the same thing, scaling up interstellar travel fantasies to imagine intergalactic voyages, is like assuming that because you can walk across a room, you can therefore walk across the Pacific. The Milky Way and Andromeda are the two dominant members of the local group, and between them they account for the vast majority of the group's total mass. They are approaching each other. Andromeda's blue shift, first measured by Vesto Slipher in 1912, tells us that the galaxy is closing the distance between us at approximately 110 kilometers per second, or roughly 246,000 miles per hour. That sounds fast. It is fast, by any human standard. It is fast enough that you might think the gap is closing meaningfully. But 246,000 miles per hour, applied against a distance of 2.5 million light years, produces a timeline measured not in centuries or millennia, but in billions of years. Even recent research has debated when or whether the two galaxies will actually merge. Even the question of whether this approach will result in a collision remains uncertain. Recent studies using the latest Hubble and Gaia data have produced conflicting results, with some simulations finding only a 50-50 chance of merger, and others restoring higher probabilities. The science is still being refined, with critical new Gaia measurements expected in 2026. But the key point is consistent across every model. Even at closing speeds of hundreds of thousands of miles per hour, the gap between us and Andromeda requires billions of years to close. Two galaxies hurtling toward each other at cosmic speeds, and the journey still takes longer than the current age of the Earth. But the key point is consistent across every study. Even at speeds of hundreds of thousands of miles per hour, closing a gap of 2.5 million light years requires billions of years. The approach velocity that sounds so dramatic becomes almost meaningless against the scale of the distance. Two galaxies hurtling toward each other at cosmic speeds, and the journey still takes longer than the current age of the Earth. This is the ladder. Each rung, a multiplication of impossibility stacked upon the rung below. The moon, a manageable leap. The sun, a difficult reach. The nearest star, a wall. The galaxy's edge, an absurdity. And then Andromeda, sitting above everything else, separated from us by 25 galactic widths of almost perfect emptiness, not merely distant, not merely far, but categorically, structurally, fundamentally removed from us in a way that makes every distance inside the galaxy feel like a local errand. And the worst part is this: we have not yet translated the distance into human time. We have not yet calculated what 2.5 million light-years actually means for a spacecraft, a signal, a human life, or a civilization. We have not yet confronted the number in its most brutal form, stripped of abstraction and dressed in the language of years, generations, and biological epochs. That confrontation is what comes next. And when it arrives, the ladder does not just reach beyond your grasp, it disappears into a darkness so deep that you cannot see where the next rung would be, even if one existed. Numbers lose their power when they grow too large. The human brain evolved to handle quantities it could see and touch. A handful of berries, a pack of wolves, the distance to the river. Maybe a few thousand, if you were counting days or stones or members of a tribe. Beyond that, numbers become abstractions. They float in the mind without anchoring to anything real. 2.5 million light-years is one of those numbers. You can say it, you can write it, but you cannot feel it. It slides through cognition like water through open fingers. So let us stop treating it as a number. Let us turn it into time, because time is the one currency every human understands. Time is birthdays, funerals, seasons, heartbeats. Time is the thing you have been spending since the moment you were born, and will continue spending until you stop. And when you convert the distance to Andromeda into time, the number stops being abstract. It becomes obscene. Start with the fastest object humanity has ever created, the Parker Solar Probe. At its closest solar approach in December of 2024, reached a velocity of approximately 430,000 miles per hour. That is roughly 120 miles every second. At that speed, you could circle the Earth's equator in under 3.5 minutes. You could reach the moon in about 33 minutes. You could arrive at Mars, at its closest approach, in roughly 3.5 days. This is not a theoretical speed. This is a real velocity achieved by a real machine, built by human hands, funded by human taxes, guided by human mathematics. It is the pinnacle of our species' ability to make something go fast. Now aim it at Andromeda. 2.5 million light-years, 14.7 quintillion miles. At 430,000 miles per hour, the Parker Solar Probe would need approximately 3.9 billion years to reach the Andromeda Galaxy. Round it for clarity. 4 billion years. 4 billion years of continuous flight at a speed that would carry you from New York to Los Angeles in under 21 seconds. The number deserves repetition because the mind refuses to hold it on the first pass. 4 billion years. The Earth itself is approximately 4.5 billion years old. The journey to Andromeda, at the fastest speed any human technology has ever achieved, would consume nearly the entire lifespan of our planet. If a Parker Solar Probe had launched from Earth the moment the planet solidified from its primordial disk of molten rock, it would still not have arrived at Andromeda today. It would still be in transit, drifting through the intergalactic void with roughly 500 million years of travel remaining. Our entire geological history, every mass extinction, every ice age, every tectonic upheaval, every evolutionary epoch that produced fish, reptiles, dinosaurs, mammals, primates, and eventually a species capable of building the probe in the first place, all of that would have elapsed during the crossing, and the probe would not yet be there. Let us try a different speed. Not an engineering speed, but a theoretical one. Suppose humanity develops propulsion technology far beyond anything currently possible. Suppose we build a spacecraft capable of traveling at 1% of the speed of light. 1%. That is roughly 6.7 million miles per hour, more than 15 times faster than the Parker Solar Probe's peak velocity. No existing or currently planned technology can achieve this speed for a crewed or uncrewed mission across interstellar distances, but it sits within the outer boundary of what physicists consider theoretically conceivable, using concepts like nuclear pulse propulsion or directed energy sails. At 1% of light speed, the journey to Andromeda would take 250 million years, 250 million years. When the probe launched, dinosaurs would not yet have gone extinct. Mammals would still be small, scurrying creatures hiding from predators. The continents would be arranged in configurations unrecognizable from a modern map. By the time the probe arrived, Earth itself might be unrecognizable, reshaped by hundreds of millions of years of geological and biological evolution. Whatever civilization launched the probe would be separated from its arrival by a temporal chasm wider than the entire age of complex multicellular life on Earth. Push the speed higher, 10% of the speed of light, 67 million miles per hour. A velocity so extreme that no serious engineering proposal has ever suggested it for a physical spacecraft. Because the energy requirements become monstrous, and the collision hazard from interstellar dust grains at that velocity would be catastrophic, each grain carrying the kinetic energy of a small bomb. But ignore those problems. Pretend the engineering is solved. At 10% of light speed, the trip to Andromeda would take 25 million years. 25 million years. That is roughly the span of time separating the present day from the late Oligocene epoch, when the ancestors of modern apes were just beginning to diverge from earlier primate lineages. The entire evolutionary arc from small tree-dwelling primates to spacefaring humans fits within the travel time to Andromeda at 10% of the cosmic speed limit. A journey that long does not belong in any category that the word travel can meaningfully describe. It is not a voyage. It is a geological process, and even light speed itself, the absolute maximum velocity permitted by the universe, does not rescue the situation. It only reveals the depth of the problem in its purest form. At exactly the speed of light, the journey to Andromeda takes 2.5 million years, no less. 2.5 million years is not a number you can contextualize through human experience, because human experience does not extend that far. Civilization does not extend that far. The entirety of what we call history, the 5,000 or 6,000 years of recorded events that constitute the full memory of our species, fits inside the light travel time to Andromeda roughly 400 times over. The light travel time to Andromeda is not a historical duration. It is a biological one. It belongs to the timescale on which species evolve, diverge, and go extinct. So let us walk backward through it. Let us stand at the present moment and step backward in time, year by year, and see what we pass as we rewind through 2.5 million years of history. This is how long the light you see from Andromeda tonight has been travelling. Every milestone we pass is a milestone that light has already outlived on its journey to your eye. Start walking backward. 500 years ago, the Renaissance was reshaping Europe. Christopher Columbus had just crossed the Atlantic. Light from Andromeda was already ancient beyond measure, but still had 500 years of travel left. 1,000 years ago, the Viking Age was ending. The Song dynasty ruled China. The light kept coming. 2,000 years ago, the Roman Empire straddled the Mediterranean. Jesus of Nazareth was alive. The light did not care. 5,000 years ago, the first cities rose in Mesopotamia. Writing was invented. History began. The light from Andromeda, already in transit for 2,495,000 years, had barely started its final approach. Keep walking. 10,000 years ago, the last ice age was ending. Agriculture was being invented independently in multiple regions. Humans were beginning to settle into permanent communities. The light had been travelling for 2,490,000 years and still had 10,000 left to go. 50,000 years ago, Anatomically modern humans were painting caves in Europe, crafting bone tools, developing language complex enough to tell stories. They were crossing oceans, colonizing new continents, reshaping ecosystems with fire and ingenuity. The light had 2,450,000 years behind it, and 50,000 remaining, a blink, an afterthought. 300,000 years ago, the earliest known Homo sapiens appeared in the fossil record in North Africa. This is roughly the full span of our species' existence. And the light from Andromeda had already been travelling for 2,200,000 years when our species was born. We are not even a footnote in the duration of that journey. We are a parenthetical remark inserted into the final entry of an encyclopedia that has been writing itself for millions of years. Keep going. 2.5 million years ago, the genus Homo had only just emerged in East Africa. The earliest members of our lineage had recently begun chipping crude stone tools from river cobbles, a behaviour barely 100,000 years old at that point. And this is precisely when the light you see tonight from Andromeda left its source galaxy. The photons departed 1 trillion alien suns during the same narrow window of geological time in which the first beings who could arguably be called human were learning to shape rocks into cutting edges on the African savanna. The entire lineage of humanity, every species of Homo that has ever existed, from habilis to erectus to heidelbergensis to neanderthalensis to sapiens, every one of them lived and died within the travel time of that light. The light is as old as our genus. It departed Andromeda within the same sliver of geological time that produced the first recognizably human species on Earth, and it arrived tonight. Every species of Homo that has ever existed has lived and died within the travel time of that light, but that walk backward through time moved in broad strides. Let us slow down and feel the full weight of the elapsed duration by placing more markers along the path, because 2.5 million years contains far more than the story of human evolution. It contains chapters of Earth's history that make our species look like a postscript scribbled in the margin. 2.5 million years ago, when the light from Andromeda began its journey, the Earth was entering the Pleistocene epoch. The planet was cooling. Ice sheets were beginning to advance across the northern hemisphere in cycles that would persist for millions of years. Mastodons roamed North America. Giant ground sloths the size of elephants browsed the forests of South America. Saber-toothed cats stalked prey across grasslands that stretched from modern-day Texas to Patagonia. The Mediterranean Sea, which had catastrophically dried out and refilled millions of years earlier during the Messinian salinity crisis, was once again a stable body of water. The Isthmus of Panama had recently closed, connecting North and South America for the first time and triggering the Great American Interchange, one of the largest migrations of land animals in geological history. The light from Andromeda departed during a world that looked like a nature documentary set on an alien planet, filled with megafauna that would not survive to greet the species that would eventually build telescopes. As that light crossed the first 500,000 light-years of void, the genus Homo was already diversifying across Africa. Homo habilis was giving way to new species, some with larger brains and longer limbs than any hominin before them. Stone tools remained crude, simple choppers and flakes struck from river cobbles, but they were spreading to new regions as early humans expanded their range across the continent. Stone tools grew gradually more sophisticated, brain volume increased, bipedalism refined. Fire may have been used opportunistically, but no language existed, no art, no symbolic thought. These were clever apes learning to survive on a changing continent, while a photon from a distant galaxy crossed a quarter of the intergalactic abyss above their heads, unnoticed and unimaginable. With 1 million light-years still remaining, the light from Andromeda had already been travelling for 1.5 million years. On Earth, Homo erectus was the dominant hominin species. They had spread out of Africa into Asia and parts of Europe. They used Acheulean hand axes, symmetrical teardrop-shaped stone tools that represented a genuine leap in cognitive ability. They may have controlled fire deliberately. They hunted large game. They persisted as a species for nearly 2 million years, an astonishing run by any evolutionary standard. And yet even Homo erectus, one of the most successful species in the history of our lineage, would be gone long before the photon arrived. At 500,000 light-years remaining, the light had been travelling for 2 million years. Homo heidelbergensis walked the Earth, ancestral to both modern humans and Neanderthals. Early evidence of shelters, of wooden spears, of coordinated hunting strategies, the stirrings of something approaching culture, though still nothing resembling language or art as we understand them. The photon was now closer to Earth than to Andromeda, but still had farther to travel than the entire width of the Milky Way multiplied by 5. At 100,000 light-years out, Homo sapiens had already been walking the Earth for 200,000 years. Anatomically modern humans had spread beyond Africa, developed specialized tools, and begun burying their dead with apparent intention. They were beginning to craft specialized tools, to use pigments, to bury their dead with apparent intention. But they had not yet left Africa in significant numbers. They had not painted caves. They had not domesticated animals. They had not invented the wheel, or the bow, or the boat. The photon had 99.996% of its journey behind it, and still had 100,000 years of travel remaining. That residual distance, the last tiny fraction of the crossing, is the entire width of the Milky Way galaxy. At 10,000 light-years remaining, humanity had built Göbekli Tepe, the oldest known monumental structure. Agriculture was spreading. Cities were forming. Writing was about to be invented. The photon was in the final 0.4% of its journey. The distance remaining was still 10,000 light-years, a gulf that light needs 10 millennia to cross, a span that contains the entire history of what we call civilization. And it was a rounding error, a decimal point, an afterthought at the end of a 2.5 million year sentence. These milestones are not decorations, they are the point. 2.5 million years is not an abstraction when you fill it with the lives and extinctions and evolutionary experiments that actually occupied that time. It is not a number when you populate it with mastodons and ice ages, and the slow, painful emergence of consciousness from the raw material of primate neurology. It is a duration that contains the entire story of everything we are. And it is the time required for a single photon, moving at the fastest speed the universe permits, to cross the gap between us and the galaxy next door. That is what 2.5 million light-years feels like when you translate it into time. Not a number, not a distance, a biological epoch. A span of time long enough for evolution to produce an entirely new kind of animal, from the first stone tool to the smartphone, from the African savanna to the surface of the moon, all of it contained within one photon's commute. And here is the detail that turns distance into something closer to imprisonment. Suppose you wanted to communicate with someone in the Andromeda galaxy, not travel there, just talk. Send a message and receive a reply. You encode a radio signal, aim it at Andromeda, and transmit it at the speed of light. The signal departs Earth and begins crossing the intergalactic void. 2.5 million years later, it arrives. Whatever civilization receives it, assuming one exists and is listening, decodes your message. They compose a reply, they transmit it back at light speed. Another 2.5 million years pass. The reply arrives at Earth. Total elapsed time for a single exchange, 5 million years. A round-trip conversation with Andromeda takes 5 million years at the fastest speed the universe allows. 5 million years ago, our ancestors had only recently diverged from the lineage leading to chimpanzees. They were early hominins, creatures part-way between ape and human, walking upright some of the time and climbing trees the rest. If a human civilization had somehow existed 5 million years ago and sent a greeting to Andromeda, the reply arriving today would reach a planet populated by beings who share no language, no culture, no institutional memory, and arguably no species identity with the senders. The civilization that sent the message would be as alien to the civilization receiving the reply as Australopithecus is to a modern-day astronaut. Communication with Andromeda is not impractical. It is incoherent. The timescale destroys the very concept of a conversation because no entity on either end persists long enough to participate in both halves of the exchange. This is the dimension of the problem that raw distance fails to convey. When you say 2.5 million light-years, it sounds like a measurement, a fact about geometry. But when you convert it to time, it becomes a fact about mortality, about the impermanence of species, about the terrifying brevity of everything we are compared to the gaps between the structures we inhabit. The distance to Andromeda is not a wall you could theoretically climb, given enough time and technology. It is a wall built from time itself, and it is taller than our species is old. Now consider what this means for the visual paradox that opened this entire story. You can see Andromeda. It is right there in the sky, a smudge of ancient light visible to the naked eye, beautiful and beckoning. Astronomers have mapped it in extraordinary detail. The Hubble mosaic resolved 200 million individual stars across its disk. We know its rotation rate, its chemical composition, its merger history, the mass of its central black hole. We have studied it for over 1,000 years. In every scientific sense, Andromeda is one of the best understood objects in the sky. We know it intimately, and yet it is separated from us by a gap that would swallow 4 billion years of travel at our fastest speed. We can see it, we can study it, we can photograph it, we can never touch it. This is also where the most recent scientific discoveries sharpen the blade of the paradox rather than dulling it. In January of 2025, the Hubble Space Telescope completed the most ambitious photographic survey of Andromeda ever attempted. The panchromatic Hubble Andromeda Treasury program and its successor, the panchromatic Hubble Andromeda Southern Treasury, combined more than 600 overlapping pointings taken over a decade of observation, requiring over 1,000 Hubble orbits to produce a 2.5 billion pixel panoramic mosaic of the entire Andromeda disk. The image resolved more than 200 million individual stars, each one a nuclear furnace burning hydrogen, many of them likely hosting planetary systems, all of them separated from us by 2.5 million light-years of impassable void. The level of detail is astonishing. Astronomers can distinguish individual stellar types, trace dust lanes threading between spiral arms, identify thousands of star clusters embedded in the disk, and reconstruct Andromeda's merger history by analyzing the ages and chemical compositions of stellar populations across the galaxy. We now know that Andromeda experienced a major merger with another galaxy approximately 2 billion years ago, an event that reshaped its structure and triggered waves of star formation still visible in the distribution of young blue stars. We know that its evolutionary history differs markedly from the Milky Way's, with a more active recent history of collisions and accretion. We know, from spectroscopic follow-up observations at the Keck Observatory, how individual stars within the disk move, how the galaxy rotates, and what that rotation implies about the distribution of mass, including dark matter, throughout its structure. Every one of these discoveries deepens our knowledge of Andromeda, and every one of them deepens the cruelty of the distance, because the more we learn, the more real Andromeda becomes, and the more real it becomes, the more painful its inaccessibility feels. This is not a vague smudge of unknown origin. This is a galaxy we have mapped star by star, whose history we can reconstruct, whose future we can model, whose internal dynamics we can observe in real time through the motions of its stellar populations. We know Andromeda better than we know most countries on our own planet, and we will never set foot in it. Meanwhile, the very question of whether the Milky Way and Andromeda will physically merge has itself become uncertain. For decades, the collision was treated as settled science, a gravitational inevitability expected to occur in roughly 4.5 billion years. But a 2025 study published in Nature Astronomy by Till Sawala and colleagues, using 100,000 simulations incorporating the latest Hubble and Gaia data, along with the gravitational influence of the Large Magellanic Cloud and the Triangulum Galaxy, found that the probability of a merger within the next 10 billion years may be only around 50%. The Large Magellanic Cloud, orbiting the Milky Way with roughly 15% of its mass, exerts a gravitational pull perpendicular to the Milky Way Andromeda orbital plane that could deflect our galaxy's trajectory enough to prevent a direct collision. A subsequent 2026 study by Wu and collaborators, using updated Gaia proper motion measurements for stars in Andromeda, pushed the merger probability back up to approximately 90% over 10 billion years, with a median merger time of roughly 6.5 billion years. The science remains unsettled, with further Gaia data releases expected in the summer of 2026 to refine the measurements. But the very fact that the outcome is debated underscores the scale of the system. Two galaxies separated by 2.5 million light-years, approaching each other at 110 kilometers per second, and astronomers still cannot say with certainty whether they will collide, because the distances and timescales involved are so enormous that tiny uncertainties in velocity and mass propagate into radically different outcomes billions of years in the future. The gap between us and Andromeda is so vast that even gravity, the most patient force in nature, takes billions of years to close it, and the outcome of that closing remains a coin flip. This contradiction between visual accessibility and physical inaccessibility is not a minor irony. It is the central cruelty of intergalactic distance. The universe lets you look. It lets you gather photons that have been crossing the void since before your species existed. It lets you build instruments that can resolve individual stars in a galaxy millions of light years away. It gives you knowledge, but it does not give you access. Knowledge and access are not the same thing, and the distance to Andromeda is the clearest proof that the universe treats them as entirely separate gifts. You may know everything about the galaxy next door. You will never go there. The light bridge connecting you to Andromeda is one-directional. Information flows in. Nothing flows out. You are an observer, permanently. A prisoner with a window but no door. And this brings us to one final calculation that deserves to sit in the mind like a weight. We have considered the journey at the speed of our fastest spacecraft. We have considered it at 1%, 10%, and 100% of the speed of light. Every result was measured in millions or billions of years. But what if we abandon realism entirely? What if we ask the most generous possible question? How fast would you need to travel to reach Andromeda within a single human lifetime? Assume a generous lifespan. Say, 80 years. To cross 2.5 million light-years in 80 years of ship time, you would need to travel at a speed so close to the speed of light that relativistic time dilation compresses the journey from the traveler's perspective. Special relativity permits this in principle. If you accelerate continuously at 1g, a comfortable Earth-like acceleration, you could theoretically reach velocities arbitrarily close to light speed. At such velocities, time aboard the ship slows relative to time in the outside universe. The traveler ages 80 years, but the universe outside ages millions. The math allows it. The physics, in principle, does not forbid it. But the energy requirements are beyond anything humanity can currently contemplate. Accelerating even a modest spacecraft to 99.9999% of the speed of light would require more energy than human civilization currently produces in centuries. And when you arrived at Andromeda, 80 years older, you would step out into a galaxy where 2.5 million years had elapsed back home. Earth would be unrecognizable. Everyone you knew would be not merely dead but fossilized, their bones compressed into geological strata, their civilizations erased, their languages forgotten. You would arrive at Andromeda as the last relic of a world that no longer exists. The journey would not connect two civilizations. It would orphan one traveler from everything they ever knew. Think about what awaits that traveler. They step out of the spacecraft 80 years older, biologically intact, mentally continuous with the person who boarded. Their memories of Earth are vivid. The faces of the people they left behind are still sharp. The language they speak is the language of the launch day. But behind them, across 2.5 million light-years of void, the Earth they remember has been dead for geological ages. The continents have drifted. The oceans have changed shape. The species that built the spacecraft, Homo sapiens, may have evolved into something unrecognizable, or gone extinct entirely, or been replaced by successor species that have no memory of ever having launched a ship toward Andromeda. Every city the traveller remembers has been ground into sediment by ice ages and tectonic shifts. Every nation dissolved, every language fossilized into silence. The traveller carries in their living memory a civilization that exists nowhere else in the universe, a ghost world preserved only inside one skull crossing the intergalactic void. Arrival at Andromeda would not be an achievement. It would be the loneliest moment in the history of consciousness, a single mind standing on the shore of an alien galaxy, with nothing behind them but extinction and nothing ahead but the unknown. Even the most exotic physics does not solve this. It only reshapes the tragedy. Time dilation can shorten the traveller's experience of the crossing, but it cannot shorten the crossing itself. The 2.5 million light-years remain real. The void remains real. The photons still take 2.5 million years to make the trip, and any physical object must do at least as badly. The universe does not offer shortcuts across intergalactic space. It offers only the hard geometry of distance and the hard arithmetic of speed, and both of them conspire to produce the same verdict. Andromeda is beyond reach. Not beyond reach in the way that the deep ocean was beyond reach before submarines, or the moon was beyond reach before rockets. Those were engineering problems. This is a physics problem. The distance to Andromeda is woven into the fabric of space-time itself, and no technology that obeys the known laws of the universe can overcome it in any time frame that preserves the identity or continuity of the travelers. So here we are, standing on a small planet orbiting an average star in an outer arm of a galaxy that contains 400 billion other stars, staring across 2.5 million light-years of void at another galaxy, equally vast, equally magnificent, burning with 1 trillion suns. We can see it. We can study it. We can measure every detail of its structure, with instruments so precise they resolve individual stars at a distance that light takes longer than the age of our species to cross. And we cannot go there. Not in a century. Not in a millennium. Not in 1,000,000 years. The nearest major galaxy, the one we call our neighbour, the one whose light decorates our autumn sky with that soft, ancient glow, sits behind a barrier of distance so absolute that it makes the boldest dreams of interstellar travel look like stepping across a puddle. And this, it turns out, is not even the most disturbing part, because the distance to Andromeda is not exceptional. It is not an outlier, not a worst-case scenario, not an unusually wide gap in an otherwise navigable universe. Andromeda is the closest major galaxy. It is the best case. Every other large galaxy in the universe is farther, most of them enormously so. If even the nearest one sits behind a wall of 4 billion years of travel time, what does that say about the rest of the cosmos? What does it say about the 2 trillion other galaxies scattered across 93 billion light-years of observable space? What does it say about the universe we thought we could someday explore? That is the question this story has been building toward, and the answer is not what you want to hear. There is a moment in every child's life when they look up at the night sky and feel the universe calling to them. The stars seem like destinations. The darkness between them seems like a sea waiting to be crossed. Every science fiction story reinforces this instinct. Warp drives, hyperspace, stargates, generation ships. The cultural mythology of space travel assumes that distance is a problem to be solved, a barrier to be broken, a chapter in a longer story that ends with humanity spreading across the cosmos like seeds on the wind. And within the solar system, within the narrow cocoon of space we actually inhabit, that mythology holds a kernel of truth. We have walked on the moon, we have driven robots across Mars. We have dropped probes onto Titan and threaded spacecraft through the rings of Saturn. Distance within the solar system is an engineering challenge, not a physical impossibility. The mythology breathes because local reality gives it just enough oxygen to survive. But the distance to Andromeda suffocates that mythology completely. It does not challenge it or complicate it or push it to its limits. It kills it. Because the distance to Andromeda is not an engineering problem awaiting a clever solution. It is a statement about the geometry of the universe itself, written in the language of space-time and enforced by the speed of light. And that statement says something that no amount of technological optimism can argue away. The nearest major galaxy is already so far that the word journey loses its meaning when applied to the crossing. If even the closest galactic neighbour requires billions of years to reach at our fastest speeds, or millions of years at speeds we cannot achieve, or 2.5 million years at the cosmic speed limit itself, then intergalactic travel is not a distant dream. It is a category error, a misapplication of a concept that works at one scale to a problem that exists at an entirely different one. Calling the crossing to Andromeda a journey is like calling the Pacific Ocean a puddle. The word does not shrink to fit the reality. It simply stops being the right word. And this is where the real terror lives. Not in the fact that Andromeda is far away. You already knew that. Everyone knows that galaxies are far away. The terror lives in the fact that Andromeda is the nearest major galaxy, and it is already this far. The distance to Andromeda is not the problem at its worst. It is the problem at its best. It is the absolute minimum intergalactic distance available to us, the shortest possible crossing to another major galaxy, and it already sits beyond any conceivable reach. This means the problem is not about Andromeda specifically. It is about the architecture of the universe. Galaxies are separated from each other by voids measured in millions of light years. That is not an accident. That is not bad luck. That is how the cosmos is built. The large-scale structure of the universe consists of galaxies clustered along filaments and walls of the cosmic web, separated by enormous bubbles of almost perfect emptiness. The average spacing between major galaxies in our region of the cosmos is several million light-years. Some are closer together in dense cluster environments, where dozens or hundreds of galaxies crowd within a few million light-years of each other. But even those crowded environments involve distances that dwarf everything inside any single galaxy by factors of tens or hundreds. The local group, our own little gravitational family, spans roughly 10 million light-years across and contains about 100 known galaxies. The overwhelming majority of those are dwarf galaxies, tiny systems containing a few million or a few billion stars, scattered through the group's volume like crumbs on a vast tablecloth. The only two major galaxies are the Milky Way and Andromeda. They dominate the group, accounting for most of its mass and virtually all of its large-scale structure. The Triangulum galaxy, the third largest member, is a modest spiral containing roughly 40 billion stars, significant but not comparable to the two giants. Everything else is small, faint and isolated. The local group is not a bustling neighbourhood. It is two mansions surrounded by dozens of garden sheds, scattered across a landscape 10 million light-years wide, and this is one of the denser galactic environments in the local universe. Beyond the local group, the distances explode. The nearest major galaxy cluster, the Virgo cluster, lies approximately 54 million light-years away. It contains over 1,300 galaxies. The nearest comparable supercluster structure, the Laniakea supercluster to which our own local group belongs, spans roughly 500 million light-years. The observable universe stretches 93 billion light-years from edge to edge and contains an estimated 2 trillion galaxies. Those galaxies are not evenly distributed. They cluster along filaments separated by cosmic voids that can stretch hundreds of millions of light-years across. Voids so empty that if you were placed at the center of one, the nearest galaxy might be invisible to all but the most powerful telescopes. This is the cosmos. Not a garden of reachable destinations, but an archipelago of island galaxies separated by oceans of nothing. Each ocean so wide that crossing the narrowest one, the one between us and Andromeda, already requires more time than our species has existed. Think about what this means for the wider universe. If Andromeda, at 2.5 million light-years, requires 4 billion years of travel at our fastest speed, then the Virgo cluster, at 54 million light-years, would require approximately 85 billion years. The observable edge of the universe, at 46.5 billion light-years, would require a travel time so vast it would take a string of zeros to write. And those are the distances to objects we can see, objects whose light has reached us. The universe almost certainly extends far beyond the observable horizon, possibly infinitely, and every additional light-year of distance adds another impossibility on top of the impossibilities already stacked to the ceiling. The 2 trillion galaxies we can detect are not 2 trillion destinations. They are 2 trillion windows. You can look through them, you can study what lies beyond, but you cannot climb through the glass. And this is where the emotional weight of Andromeda's distance settles onto the chest and refuses to lift, because the universe is beautiful, staggeringly, heartbreakingly beautiful. Hubble, Webb, and ground-based observatories have shown us galaxies in every stage of evolution, from chaotic proto-galactic clumps in the deep field images to grand design spirals with arms as elegant as calligraphy. We have seen galaxies colliding in slow-motion gravitational dances that last hundreds of millions of years. We have seen starburst galaxies igniting with the fury of millions of simultaneous stellar births. We have seen elliptical galaxies glowing with the amber light of ancient stars that formed when the universe was young. We have seen lenticular galaxies, ring galaxies, irregular galaxies shaped by collisions and tidal forces into forms that look like cosmic abstract art. The universe is an endless gallery of structure and light and motion, and every piece in the gallery is locked behind a barrier of distance so extreme that observation is the only relationship we will ever have with it. Andromeda is the one piece we can almost pretend is close. It is the galaxy we point to when we want to feel connected to the larger cosmos. It is the galaxy we include in collision simulations, the one we say will merge with our Milky Way someday, the one that makes us feel like participants in a galactic story rather than isolated spectators. And all of that is true in a sense. The Milky Way and Andromeda are gravitationally bound. They are approaching each other. Whether they collide in 5 billion years or 10, or merely pass each other and loop back, as the most recent studies suggest is possible, they are part of the same gravitational system. But gravitational interaction is not the same as accessibility. Two objects can be gravitationally bound across a distance that no physical traveler could cross within any meaningful time frame. The Moon is gravitationally bound to the Earth and we can reach it in 3 days. Andromeda is gravitationally bound to the Milky Way, and we cannot reach it in 4 billion years. Gravity connects them. Distance isolates them. Both facts are true simultaneously, and the second one is the one that matters for any question about what humans can actually do. Here is another way to feel the weight. Consider what you are seeing when you look at Andromeda on a clear night. You are seeing light that left that galaxy 2.5 million years ago. You are looking at the past, not the recent past, the deep past. The Andromeda galaxy you observe tonight is the Andromeda galaxy as it existed before the genus Homo emerged on Earth. If an observer in Andromeda aimed a sufficiently powerful telescope at our planet right now, they would not see human civilization. They would not see cities or agriculture or language. They would see a world populated by Australopithecus and early Homo species, chipping stones and avoiding predators on the African savanna. That is the temporal displacement created by 2.5 million light-years. It does not merely separate 2 points in space, it separates 2 points in time. Andromeda as it exists right now, at this very moment, is invisible to us. We will not see the Andromeda of today until 2.5 million years from now, long after every human alive today has been dead for longer than civilization has existed. This temporal isolation compounds the spatial isolation in a way that makes the word neighbor almost cruel. You do not just live far from your neighbor, you live in a different era. The Andromeda you see is ancient. The Andromeda that exists is unknown. The two are separated by a time gap so vast that no meaningful real-time relationship between the galaxies is possible. We are neighbors in space and strangers in time, and the distance between us enforces both forms of separation simultaneously. Now return to the central question this story was always building toward. What does the distance to Andromeda actually mean? Not as a number, not as a travel time, but as a truth about the universe and our place within it. Because the real revelation is not that Andromeda is far. The real revelation is what Andromeda's distance tells us about everything else. If the nearest major galaxy sits behind a wall of 2.5 million light-years, then the universe is not a space we move through. It is a space we look at. The observable cosmos, with its 2 trillion galaxies and its trillions of stars, is a panorama, not a territory. It is something we can map, photograph, study and admire, but not something we can inhabit beyond our own tiny galactic corner. The distance to Andromeda draws a line. On one side of that line sits everything we can plausibly reach, even in the most wildly optimistic projections of future technology, the nearest stars. Maybe, in some unimaginably distant future, the nearest regions of our own galaxy. That is the reachable universe. It is a bubble perhaps a few hundred or a few thousand light-years in radius, an almost invisibly thin shell wrapped around one ordinary star in one outer spiral arm. On the other side of the line sits everything else. Every other galaxy, every other galactic cluster, every structure in the cosmic web, every world, every star, every possible civilization that exists outside our local bubble. All of it is visible. All of it is knowable through light. None of it is reachable. And Andromeda is the closest thing on the far side of that line. And the line is not holding, it is retreating. The isolation that Andromeda's distance represents is not a fixed condition of the cosmos. It is a worsening one. Because the universe is expanding, and that expansion is accelerating, driven by dark energy, a mysterious repulsive pressure that constitutes roughly 68% of the total energy content of the cosmos. Within the local group, gravity is strong enough to resist this expansion. The Milky Way and Andromeda and their retinue of dwarf satellites are gravitationally bound, falling toward each other despite the stretching of space around them. But beyond the local group, dark energy wins. Galaxies outside our gravitational family are being carried away from us by the expansion of space itself, and they are receding faster the farther away they are. The Virgo cluster, 54 million light-years distant, is receding at roughly 1,100 kilometers per second. More distant structures move faster still. At a distance of approximately 14 billion light-years, the recession velocity reaches the speed of light. Galaxies beyond that threshold are moving away from us faster than light can travel, not because they are physically moving through space at superluminal velocities, but because the space between us and them is stretching faster than photons can cross it. This means those galaxies are already beyond our reach, not merely beyond our ability to travel to them, but beyond our ability to ever communicate with them, even in principle, even with signals moving at the cosmic speed limit. Light we send in their direction will never arrive. Light they send in our direction will never reach us. They have crossed the cosmological event horizon, a boundary defined not by a wall or a barrier, but by the geometry of expanding space-time itself. And every day, more galaxies cross that horizon. Cosmic expansion is carrying objects beyond our causal reach at an accelerating rate. The observable universe, the sphere of space from which light has had time to reach us, is not growing fast enough to compensate. The number of galaxies we could theoretically influence or communicate with is shrinking, not growing. The universe is getting lonelier. The implications over cosmic time are staggering. In roughly 100 billion years, every galaxy beyond the local group will have receded beyond the observable horizon. Future astronomers, if any exist, will look out into the sky and see nothing but the merged remnant of the Milky Way and Andromeda and its attendant dwarfs, floating in an apparently empty cosmos. The cosmic microwave background radiation will have been stretched to wavelengths too long to detect. The evidence for the Big Bang, for cosmic expansion, for the existence of other galaxies, will have vanished. A civilization arising in that era would have no way to discover that the universe was ever anything other than a single galaxy surrounded by infinite empty darkness. The knowledge that we possess today, knowledge of 2 trillion galaxies and a cosmos 93 billion light-years across, will be physically inaccessible to them, not hidden, not encrypted, erased by the expansion of space itself. This future desolation matters for the story of Andromeda, because it reveals that the isolation we feel now, the horror of realizing that even the nearest major galaxy is beyond meaningful reach, is not the full picture. It is the beginning of a process that ends with total cosmic solitude. Andromeda is the one major galaxy we will ever interact with, because it is the only one close enough and gravitationally bound tightly enough to resist the expansion that is pulling everything else away. In a sense, the merger of the Milky Way and Andromeda, whenever it occurs, is not just a collision. It is a consolidation. The universe is handing us our final companion, and then slowly, inexorably, removing every other galaxy from the sky. What remains after the merger, the combined elliptical galaxy, sometimes called Milkomeda, will be our permanent and only home. The nearest major galaxy beyond the local group is already millions of light-years away and getting farther every second. Andromeda is not just our nearest neighbour. It is, for all practical and physical purposes, our last one. This is what makes the distance to Andromeda terrifying rather than merely impressive. It is not the size of the number. It is what the number reveals about the boundary between knowledge and experience. Humanity can know the universe. We have proven that beyond any doubt. We can detect galaxies 13 billion light-years away. We can measure the cosmic microwave background radiation left over from the birth of the cosmos. We can infer the existence of dark matter and dark energy, substances we have never directly observed, through their gravitational effects on visible structures. Our knowledge of the universe is vast, precise, and growing, but our experience of the universe is confined to one galaxy, one island, in an archipelago of 2 trillion. And the nearest neighbouring island is already so far that crossing to it would take longer than our planet has existed. There is a philosophical tradition that finds comfort in cosmic scale, the overview effect, experienced by astronauts who see Earth from orbit, often produces feelings of unity and transcendence. The knowledge that we are small can feel liberating, a release from the petty concerns of individual life into a larger perspective that encompasses stars and galaxies and cosmic time, and there is real beauty in that perspective. The universe is magnificent, its structures are elegant, its processes are awe-inspiring, but the distance to Andromeda introduces a different emotional register. Not awe, not wonder, something closer to grief, because the distance tells you that the magnificence is real but untouchable. The universe spread its galaxies across a canvas so large that no single species, no matter how intelligent or technologically advanced, could ever visit more than an infinitesimal fraction of the whole. The cosmos built cathedrals of light, and then surrounded each one with moats of emptiness, millions of light-years wide. It created a universe worth exploring, and then made exploration, in any galactic sense, physically impossible. This is not a limitation of human technology, it is a limitation of physics. The speed of light is not a speed limit that might someday be bypassed with better engineering. It is a fundamental property of space-time. Nothing that carries information or mass can exceed it within the framework of general relativity, and general relativity is the most thoroughly tested theory in the history of science. Speculative concepts like wormholes and warp drives exist as mathematical curiosities within the equations, but no physical evidence suggests they can be realized, and the energy requirements for even the most favorable theoretical models exceed the total energy output of stars. These are not doors waiting to be opened. They are equations waiting to be constrained by experiments that will almost certainly show they cannot describe real constructible objects. And so the universe remains what it has always been, an immensity that allows observation but forbids participation, a gallery whose paintings you can study but never enter. The distance to Andromeda is the first and most visceral expression of this truth, because Andromeda is the closest major galaxy, and it is already impossibly far. If the nearest painting is already behind glass so thick you cannot break it, then every other painting in the gallery is behind glass thicker still. The universe is not withholding intergalactic travel as a challenge to be overcome. It is expressing, through the geometry of its own structure, a fact about the relationship between matter, distance, and time that no amount of ingenuity can overrule. And yet Andromeda is approaching. This is the final paradox, the last twist that makes the story complete. Despite everything we have established about the impossibility of crossing the gap is closing on its own. Andromeda is moving toward the Milky Way at roughly 110 kilometers per second. The two galaxies are gravitationally bound and have been drawing toward each other for billions of years. Whether the outcome is a direct collision and merger, as models long predicted, or a series of close encounters and eventual coalescence, as the most recent simulations suggest, the result is the same. Billions of years from now, the two galaxies will interact, their stars will intermingle, their structures will reshape. The two largest members of the local group will become one, but that merger, when it comes, will not be a journey. No one will travel from here to there. No consciousness will cross the void. The galaxies will simply fall together under gravity, a process as mindless and impersonal as water flowing downhill. The stars of both galaxies are so widely spaced that virtually none of them will physically collide. Our Sun, if it still exists, will be relocated to a different orbit within the merged structure, but it will not be destroyed. The night sky will change. Andromeda's stars will appear as individual points of light scattered among our own. Two island galaxies will become one, and the 2.5 million light-years that once separated them will be compressed to zero, not by technology, not by ambition, not by human effort, but by the slow, patient, indifferent work of gravity operating across cosmic time. There is something almost mocking in that. The distance that is utterly impassable to any traveller will be erased by the universe itself, simply because it has billions of years to work with and no consciousness to grow impatient. Gravity does not care about the distance. Gravity does not feel the weight of 2.5 million light-years. It simply pulls, second by second, millennium by millennium, epoch by epoch, until the gap closes. What is impossible for any living being is trivial for the cosmos. The universe can cross its own distances. We cannot. And that, in the end, is the terrifying truth this story has been building toward. The distance to Andromeda is not a fact about one galaxy. It is a fact about every galaxy. It is a fact about the structure of reality itself and the place of conscious beings within that structure. We live in a universe that permits intelligence, permits curiosity, permits the construction of telescopes and the measurement of cosmic distances, but does not permit the crossing of those distances on any scale larger than the local. We can see the universe. We can understand it. We can map its structures to the edges of the observable horizon. But we cannot enter it. We are confined to one galactic island, surrounded by an ocean of distance that no ship, no signal, no technology bound by the laws of physics can meaningfully cross. Andromeda hangs in the autumn sky tonight, the same faint smudge of silver light that Al-Sufi recorded 1,000 years ago. It looks close. It looks like a destination. It looks like the kind of place a sufficiently advanced civilization might someday reach, given enough time and ambition and ingenuity. But the light telling you it is there has been travelling for 2.5 million years, and when it reaches your eye, it carries a message that most of us spend our lives refusing to hear. The galaxy next door is not next door. It is 2.5 million light-years away. It is 4 billion years away at our fastest speed. It is separated from us by a void so wide and so empty that the entire history of the human species fits inside the travel time of a single photon crossing it, and it is the closest one. Every other major galaxy in the universe is farther. Many are millions of times farther. The cosmos built its galaxies and then placed them at distances that turn the spaces between them into walls no living thing can climb. You're standing on a rock orbiting a star in a galaxy that contains 400 billion other stars. Across 2.5 million light-years of darkness, another galaxy burns with 1 trillion suns. You can see it with your naked eye on any clear autumn night. It is the nearest major galaxy in the universe. And it is so far away that the word nearest means nothing, and the word journey means nothing. And the distance between you and the galaxy next door is not a gap to be crossed, but a boundary to be accepted. The universe is not a room you can walk across. It is an ocean you can see the far shore of but never swim to. And the far shore begins at Andromeda, 2.5 million light-years away, visible, beautiful, knowable, and forever out of reach.